Okay, in this video, we're going to go over balancing complicated redox reactions. It's a pretty tricky topic. It's not the most point-efficient topic on the IB exam. It does take a decent amount of time to do this carefully, and usually it's only worth a mark or two. But it does kind of relate to a number of the topics in the redox chapter, so it's going to be important. I'm going to go through this mnemonic, this NORSE mnemonic that I made up, but I'm going to kind of show the need for it first. So I've added these couple of pages in. They're not in your current handout. If you look at this first reaction, so it's an unbalanced reaction. Copper plus Ag plus makes copper 2 plus and Ag. Upon first look, it might look like everything is balanced, but it's not balanced, and it's sort of an example of why, unless you know the steps, you could get tricked into not balancing a redox equation. So when we consider redox equations or any equations, we know they need to be balanced for atoms, but also for charge. And what I mean by that is, if you take a look at this equation, there's a total of one positive charge on the left, one net positive charge from that Ag, but on the right, there's two positive charges. So that doesn't make any sense. All of a sudden, you've created an extra positive charge. We know we don't really create new charges or new matter, so there's something wrong there. So the key to balancing redox equations is splitting them up into half equations. Half equations mean that we're going to look at oxidation and reduction one at a time. Okay? And in these half equations, we are going to show electrons being lost and gained. So we're actually going to see electrons in the half equations. Okay? Pull this up a little bit. So what would that look like for this reaction? Well, if I copy it for a second, bring it down here. Let's just look at the oxidation. So the oxidation is where the oxidation number is increasing, and that would be copper. So copper is getting oxidized, going from copper 0, normal element, to copper 2 plus. That implies that the copper lost 2 electrons. The way I represent the loss of electrons is by putting them on the right-hand side of the equation. It's more or less like saying, okay, well, I started as copper. Afterwards, I'm copper 2 plus, and these are the two separate electrons. Okay, so electron loss is always represented with electrons as a product. They're being given away. So this is the oxidation half equation. If I want to do something similar, well, let's see if we can do this quickly. We're going to paste that equation again. This time I'm going to get rid of the stuff with copper. And in this equation, I got Ag plus. It's not, so going from 1 plus down to 0, that's reduction. In order for that to happen, each silver must gain an electron. So one electron given to this silver would make it regular silver, silver metal. And so now that we've got these two half equations, you might be able to see why they're not balanced. We're saying that copper gets oxidized and loses 2 electrons, but then silver only gains 1. That means 1 electron is just disappearing. And that's why the half equations are so helpful. They show the electron trade, the electron transfer. And so any redox equation has to be balanced for electrons. So 2 electrons times 2 times 2. So if I am going to multiply the number of electrons, I have to multiply everything else in the equation by the same number. And now I'm losing 2 electrons and I'm gaining 2 electrons. So it means the electrons being lost and gained are balanced, and that means the equation is going to be balanced. So now if I add these equations together, these half equations, you can see that the electrons cancel out. Anything on both sides of the equation, I'm losing 2 and then I'm gaining 2. Although that does happen, net, that actually doesn't take place. We don't have to write it into our overall chemical equation. So if this is going to be my overall chemical equation, now what has happened is that 2Ag and 2Ag, if I wrote those electrons in just for a second, we would see that there's 2 on that side and there's 2 on this side, and that means that they sort of cancel, just like in math class. If you have the the same stuff on both sides of the equation, you can cancel it out. So electrons should not show up in a final redox equation, but they should show up in the half equations. So this here with the 2's on each side is now a balanced redox reaction. And if you count up the charge now on this side, there's now 2 pluses total from the 2 Ag1 pluses. And over here, there's 2 pluses total for the copper 2 pluses. Okay, so that was actually a relatively simple redox reaction to have to balance. So if we take a look at this next one, you can see it gets a little bit trickier. We've got ions changing, we've got hydrogens and oxygens in a bunch of places, we've got nitrogens, and the nitrogen is in this polyatomic ion and then this molecule. It's going to be definitely more complicated. So in that case, we're going to want to use that mnemonic. I'm going to pause just for a minute. So here's my mnemonic to help you stay organized when you're balancing redox equations. I call it NORSO. It could maybe be called SORSO. We could use a big S here for states instead of numbers. On the old syllabus, it was a little bit more okay to refer to oxidation states as oxidation numbers, but you'll get the idea anyways. So essentially, this is just to give you sort of a procedure to walk through when you try to balance the equations to keep yourself organized. So some of the steps don't occur or aren't necessary for every type of redox equation. And I've starred those here, like the step about subscripts, oxygen and hydrogen, for example. In the last equation that we just balanced with copper and silver, we didn't use those steps. We did, however, do these steps. The first thing you should always do trying to balance a redox equation is put in oxidation states or the oxidation numbers. Use those rules that we've talked about, figure out everything's oxidation state. That should make it pretty easy to spot what's been oxidized and what's been reduced. You're looking for the increasing oxidation number for the oxidation, and you're looking for the decreasing oxidation state for the reduction. You're going to write out half equations showing electrons being lost and showing electrons being gained. If there's a subscript involved, then we'll include it at this point. We're going to skip this step for the video, and we'll talk about it in class. And once you've got your 2 half equations, then you need to balance the electrons for the half equations, which is what we did in the silver copper example. We multiplied through by 2, and that made 2 electrons lost, 2 electrons gained, and that's what I mean by balancing electrons. After that, there are 2 steps that we need in a lot of redox reactions. There's often some oxygen and hydrogen involved in the reaction, maybe as H+ ions, maybe as water, maybe attached to something else. Usually, these elements are not involved in the sort of the redox part of it, the oxidation and the reduction, but they are still involved in the chemical reaction. And so we do need to balance them. Usually this will be given to you, or you'll be told that the reaction is taking place in acidic solution, which means that there's plenty of water around and there's plenty of H+ ions around. So that's a good thing to remember. If you're ever told that you're doing something in acidic solution, what that means is that you can use H+ ions, because acid is more or less equated to H+ ions, and you can use H2O molecules to help balance the equation. Because in acidic solution, there are lots and lots and lots of water molecules, and there are lots and lots and lots of H+ ions. So you're allowed to add those to the equation as needed to keep it balanced. So the best thing to do to try to use NORSO is to see how it's worked in practice. So here's another example. I'll move that one out of the way. We got this second redox reaction to look at here. So if we put in oxidation states, we're going to see that this iron over here is 0 because it's just an element. This nitrogen is +5. I'm going to go quickly because we did this one in class and for the sake of the video. This is iron 3+. Over here, this is nitrogen 2+. And oxygen is -2 and hydrogen is +1. So if we're looking at the changes, I can see that the oxidation, the increase in oxidation number, is going to be from iron 0 to iron 3+. So I'm going to write out my oxidation half equation. So it would start with Fe going to Fe3+. And now to make it balanced for a charge and to show the oxidation, I'm going to put those 3 electrons on the right-hand side. For the reduction, it looks like the nitrogen +5 is getting reduced, and it's going to turn into nitrogen +2. And that looks like a decrease by 3, which means that must have taken 3 electrons to be gained on this left-hand side. So we've got nitrogen +5, nitrogen +2, and I've got the electrons. So notice that even though nitrogen comes with oxygen, I've ignored it for the time being. So when we do the NORSO steps and we look at oxidation and reduction, at first we're just going to look at the elements that are being oxidized and reduced. Okay, so I'm kind of building back my half equations and building back my total equation. So I've got iron and I've got nitrogen. I've got oxidation and I've got reduction. Okay, there's no subscripts to worry about in this reaction, so we don't need to do S. And in fact, this equation is pretty easy in that the electron trade was actually balanced. So we've done all of NORSE. We've done our states, we've done oxidation reduction, we skipped this step, and we balanced the electrons. Now we need to check, is there any oxygen or hydrogen involved that we haven't balanced? Okay, and I would say yes, there is. I totally ignored this O3, and I ignored this O, and I haven't dealt with the water or the H yet, and we're going to deal with those last. So if you look at the iron, iron and iron 3+ doesn't have any oxygen attached. So this is actually a completed oxidation half equation. So this is the oxidation half equation. It's totally done. We don't need to do anything else to that. Okay. But this is not complete as a reduction half equation. And that's because I've been ignoring that oxygen. Okay. So at this point, I'm going to add that back in. So now I'm going to add the original equation back together, but I'm going to leave those electrons there. So there's oxygen, and there was oxygen. Okay, so I know that the 3 electrons are there from what I did before. Now I need to balance the oxygen as well. So I've got 3 oxygens on the left, and I've only got 1 on the right. I don't want to change the coefficients on the N, on any of the things with N in it, because that would, if I double this or triple this over here, then I'm going to need to triple this, and that's going to change the number of electrons. And that's already balanced, 3 and 3. So what I'm allowed to do, because I see that there's water and hydrogen allowed, the way that I balance oxygen out is by adding waters to the other side of the equation where I need more oxygen. So there's 3 oxygens here on the left, there's 1 on the right so far, which means I need 2 more waters. Okay? By having 2 more waters, that gives me 2 more oxygen atoms, and now I have 3 oxygens on both sides. Problem is now I just created 4 H's, and to keep that balanced, I need to put 4 H pluses on the left. Okay. Now, if this is your first time seeing this, you might say, well, how come you're just allowed to do that? Well, again, what I mentioned was the questions tend to tell you that this is taking place in acidic solution. So you're not really making things up. You're just using the scenario to help you fill out and balance this equation. So now I've balanced N, I've balanced the O's, and I've balanced the H's. And so now I've got my reduction half equation completed. If you put these 2 things together, you add them up, the electrons will cancel. Okay, so 3 and 3. Nothing else cancels. And so we end up with the equation that we had at the top, except now we have a 4 here, and we have a 2 here. And now it's totally balanced. Okay. Last one, try to make it snappy. Okay, we've got this thing down here. So again, I'm looking for oxidation and reduction. I'm looking for an increase, and I'm looking for a decrease. I also need to put in my oxidation states. So this is a 2+. In here, this Mn has a +7 oxidation state, another one that we did in class, so +7 for Mn. I don't need to worry about O or H. Iron is 3+, and Mn is 2+. So I can see that the oxidation is the iron 2+ going to iron 3+. And if it's going from 2 to 3, that's only a change of 1, and the electron goes on the right-hand side. I know that it goes on the right-hand side because, well, if we are increasing our oxidation state, oxidation is losing electrons. That's how I show losing electrons. You can also double check. There are 2 pluses on the left-hand side of the arrow, and total, there's 2 pluses on the right, 3 plus the 1 minus. So charge is always balanced, even in these little half equations. The next one, I'm just going to look at that Mn. I'm going to look at Mn plus 7, turning into Mn 2 plus on the right-hand side. Well, that's a change of 5, and it's going down by 5, which means I need 5 electrons to make that happen. Okay. So if you check on the left, total, there's 2 positives, net charge. On the right, 2 positive. So now we've done this. Again, there's no subscript step here. I avoided that for the first video. Now we've got to balance electrons. So 5 electrons here, 1 electron there. That means I need to multiply everything in this equation by 5. Okay? And now I've got 5 electrons being lost and 5 electrons being gained. So electrons are balanced. I've finished off all of my NORSE steps. So the last 2 steps are the oxygen with water and the hydrogen with H pluses. Iron 2 plus doesn't have any oxygen with it, neither does iron 3 plus, so this equation is all set. So I'm going to look at this one. I'm going to add back in those 4 O's that were there and that minus charge and try to make it look like it did originally. There's the MnO4. Mn2 plus doesn't have any oxygen. So here's what we're dealing with. I have 4 oxygens on the left and none on the right, which means I need to add 4 waters to make this thing balanced. Okay, so for every oxygen I need 4. I add 1 water because there's 1 oxygen per water. So now oxygen is balanced on each side. Now I do H's. There's now 8 hydrogens on that side, so I've got to have 8 hydrogens on this side. For every hydrogen I need, I simply add an H plus ion, and now the equation is balanced for Mn, it's balanced for hydrogen, and it's balanced for oxygen. And now we're done. I've got the oxidation half equation up top, and I've got the reduction half equation on the bottom. If I want to cancel out those electrons, they go away. Nothing else cancels. And so in this case, the final balanced equation, I'll go back to this one and edit it. There's a 5 in front of the irons. There's an 8 in front of here. There's a 5. And our poor water that got squeezed out is a 4. And you can see that this would have been really, really hard to balance without these steps. It's hard enough with these steps, but if you didn't have these steps, you kind of wouldn't even know where to begin. But NORSO helps walk you through it, making sure that you get the correct coefficients. While I've got you here, the last thing I want to cover is something called oxidizing and reducing agents. So we've already talked about what gets oxidized and what gets reduced. In this first equation, we talked about how copper got oxidized and Ag plus got reduced. That was because the oxidation state went up, and that was because this oxidation state went down. We could do similar things for these other ones. We talked about how iron was the thing that got oxidized because its oxidation state increased. It lost electrons. And here it was N plus 5. I'll just write it like that for the time being. That got reduced down to N plus 2. And in this one, we had the iron plus 2 getting oxidized. And here we had the Mn plus 7 getting reduced. So far we've talked about things as getting oxidized, getting reduced. And that's fine. That's a valid question that does get asked. But sometimes you get asked to look at it in a different way. So getting oxidized and getting reduced, it's kind of like a passive way of looking at the equation. Copper got oxidized. A flip way to look at it is to look at it as what is causing the reduction, what is causing the oxidation. It's a little bit confusing at first, but if you think about it, if copper gets oxidized, it loses electrons. Well, who gains those electrons? Ag+. That's what causes it to get reduced. So when copper loses, it also causes the gaining of electrons, so it causes gaining electrons. If something causes gaining of electrons, it's causing reduction. So on the one hand, you could say copper has gotten oxidized, but you could also say that copper is acting as the reducing agent, the species that is causing something else to gain electrons, to get reduced. In the same way, Ag plus gets reduced, it gains electrons in the reaction. But if it gains, well, something else must have lost. That means it caused the loss of electrons. And if you cause the loss of electrons, you cause oxidation. And therefore, you can be called the oxidizing agent, the species, the reactant that caused the oxidation. So oxidizing agents and reducing agents are always reactants, and it's pretty much a flip. So if something was oxidized, it's going to be the reducing agent. Okay? It loses electrons, which means it causes something else to gain electrons. If you get reduced, you end up acting as the oxidizing agent, because if you gain electrons, that means you sort of steal them from something else. You cause loss. Okay? So we'll see that again down here, more or less the same. So iron got oxidized, which means it was acting as the reducing agent. And then N plus 5 got reduced. The only thing that changes here is that instead of saying N plus 5 is the oxidizing agent, we say nitrate is the oxidizing agent. So it's the thing that has N plus 5 in it, but anytime you identify an agent, it's always the whole species from the equation. So because it looks like nitrate in the equation, it has to look like nitrate here when I talk about it as an agent. Iron just looks like iron, and so that's why it's okay to just list it as Fe. So for this last one, you got Fe2 plus, and again, we're going to say whatever got oxidized is the reducing agent. I look up here, it's just Fe2 plus, so Fe2 plus, that's our reducing agent. And Mn plus 7, I'm going to bring that up here to the oxidizing agent. But again, I have to check the equation. It looks like Mn was part of something else, and therefore it's not Mn plus 7 that I would call the oxidizing agent. It's the whole manganate 7 ion, the permanganate ion, that would get called the agent. So there's this funny sort of backwards relationship between what got oxidized is also the reducing agent, what got reduced is also the oxidizing agent. That is, it can be very confusing. I understand that it's backwards, but if you think through what the definitions are, it actually does sort of make sense. So what I want you to do now, if you've watched this video, you've taken your notes, I want you to go to the next page, and there's this thing right here. We've got copper reacts with nitrate in the presence of acid, right? So we know that. What that means we can use H plus ions. There's water, nitrogen monoxide gas. So nitrogen monoxide is NO. Just make sure we know the formulas. Nitrate is NO3 minus. In case you didn't remember, I want to make sure you can focus on balancing the redox equation. Okay, so we've got copper metal, Cu, copper 2 plus ions. All the reactants and products are described. The NORSE steps are written here to remind you. There's no subscript step here, so I'll delete it for now. And give this balancing one a try for the rest of your homework, and we'll go over the answer in class on Friday. Thanks a lot.